Okay, in this section, we're going to look at a different way of constructing a solid. Okay, in the last section, we looked at volumes of rotation, where we're essentially building up a solid by stacking up all these disks, where the radius of the disk is defined by some function. In this section, we're looking at defining the base of the solid with some function, and then building up slabs that of known cross section. Okay, so like they could be, the cross sections could be squares, or they could be equilateral triangles, or isosceles triangles, or they could be semicircles, or something like that. So let's dive in to an example to see what we're talking about. So in this example, we have a solid that has a circular base. Okay, so I'm just going to draw this base. All right, so we have a circular base. All right, and then we're going to build up a solid by putting equilateral triangles on top of this circular base. Okay, so, and these triangles are, let's see, they're perpendicular. Okay, well, and they're perpendicular cross sections, okay, that are all triangles. So I'm going to superimpose a coordinate axis here, okay? And so this is a circular base of radius 1. So we're talking about x squared plus y squared equals 1, okay? And now, in the case of a circle, it really doesn't matter whether these cross sections are parallel to the x-axis or the y-axis, or if they're diagonal, because there's, the circle has total symmetry. But just to make things easy, I'm going to make these equilateral triangles parallel to the y-axis, so perpendicular to the x-axis. All right, so the base of these triangles is going to sit on the circle this way. So the distance here is y, the distance here is y. So essentially the base of each one of these equilateral triangles is going to be 2y. All right, so let me put in some numbers here. This goes from 1 to -1. And so, since we're making these cross sections perpendicular to the x-axis, we're going to integrate it across. We're going to try to build up all these slabs across that are equilateral triangle size, but the size of the triangle, the size of the equilateral triangles is going to get smaller and smaller the closer we get to the ends. Because you can see here, when we build up that equilateral triangle, it's going to have a base that's a lot shorter than the one over here that I drew. So, all right, let's try to. It's really tough to visualize what these look like, but sometimes it's kind of nice to like try to lay down the axis. So I'm going to draw here. It's an x-axis, and I'm going to try to like flip this down so it's laying flat. So I'm trying to draw something that looks three-dimensional now. So all right, so there's my xy axis axes laying down. And here's my circle. Let's see if I can draw my circle in here, laying down on this xy coordinate plane. And then essentially these equilateral triangles are going to be sticking up in the perpendicular direction. Okay, and they're equilateral, so I'm going to make, and the base is a triangle. So it's going to look something like that. Okay, that's not too bad. But each one of these is going to have some thickness. So let me draw something that has some thickness here, because these are going to be like some kind of triangular slabs. So there's what the one across the middle looks like. Now if I drew one here that's a little closer, oops, I want to make this parallel to the y-axis, right? So this is what a triangle would look like closer to the edge. It's going to be smaller, right? So so a triangle here might look something like, I didn't draw that very well, but you get the idea. Okay, so there's like a triangular slab. So they're going to get smaller the closer they get to the edge. So it's going to end up having this sort of fin-like shape. Now it's really hard to draw these things. So, you know, it's going to have this circular base, right? I could draw my axes across here and here. So I'm trying to draw the circular base, and it's going to have this triangle that sticks up, right? And it's going to taper down, right? So that the tops of all these triangles are going to kind of fall along this curve, right? And so it's going to have sort of this fin shape. I don't know if that looks anything like a fin, but it's really hard to draw in 3 dimensions, especially with this pen that I'm using on the computer. So, all right. Well, okay. So what we need to do is add up a bunch of equilateral triangle shaped slabs. So let's look at one equilateral triangle so we can find the cross-sectional area of an equilateral triangle, and then we can look at how we add these up. So again, like I said, the base is going to be 2y, right? So if this is going to straddle the x-axis, and it's going to go y up and y down. So the base of the triangle is going to be 2y. And if you remember, you know, we have a 30-60, or well, we have a 60 degree angle. So it's equilateral triangle. So this triangle here ends up being a 30-60-90, right? So this is 2y, and this is square root of 3 times y. Is the height of the triangle. Okay, so the area of this triangle is going to be 1/2 base times height. So let me write this down. Area is equal to 1/2 times the base, which is 2y, times the height, which is the square root of 3y. Okay? Now let's simplify that, because 1/2 times 2 is just 1. So we're going to end up with the square root of 3 y squared, right? When we multiply that out. But now we're integrating in the x direction, because our thicknesses are delta x, right? Because we've got these slabs are all perpendicular to the x-axis. So we're going to integrate in the x direction. So we really need our expression in terms of x. So let's rewrite the equation for the circle in terms of x. So if I rearrange this, I get y is equal to the square root of 1 minus x squared, right? And so, of course, squaring the square root, then I'll end up with the square root of 3 times 1 minus x squared, right? Because I'm squaring the square root. So I just get 1 minus x. All right, so I have the area of each of the triangles as we're going along, and I'm going to want to integrate that. So I'm going to integrate from -1 to 1, square root of 3, 1 minus x squared dx. All right. Now I'm going to actually make this a little simpler. I can also write that as 2 times the integral from 0 to 1 of the same thing, square root 3, 1 minus x squared. So I'm just taking advantage of the symmetry of the circle, right? I can, instead of integrating from -1 to 1, I'm just going to integrate from 0 to 1 and then double it. Okay. All right. So now we just need to do this integral. So what do I get? I'm going to get 2 square root 3 if I pull the square root of 3 out, and then when I integrate 1, I get x, and I integrate x squared, I'm going to get 1/3 x cubed. I'm going to evaluate that now from 0 to 1. And so what I end up with is 2 square root 3, and I'm going to get 1 minus 1/3. So 1 minus 1/3 is 2/3. 2/3 times 2 square root of 3 becomes 4 square root 3 over 3. All right? And there we go. That's the area.